China that are dominating that field. But recently, Prime Minister Modi announced a national quantum mission and devoted 6,000 crores to that field. This year, the Nobel Prize in Physics went to Anthony Zeilinger, who's a quantum physicist. And, that brings us very close to the beginnings of why we should be debating and discussing and at least getting familiar with this topic. And to unravel, as I said, all of that for us, we have someone fantastic who herself is in the news because she conducted an experiment which, as I said, questions the fundamental notions of our reality. It also put us somewhere on the map, an experiment that almost equals what Zeilinger won the Nobel for. I'm going to ask her to help us, understand and decode all that. But I just wanted to again share just one or two facts, which is that this is a field, a nascent field, where we were talking about AI and what AI can do so fast and what AI can do so exhaustively. But here comes a new technology which can do all of this 185 million times faster than the supercomputers that already exist. How can we not engage with it? The existing commercial computers, which are like below the level of infancy, just today, if you look up Google, China spoke about a new computer which has done in 1 minute, less than 1 minute, 2 lakh computations which it would take a supercomputer to take 5 years to do. And that's this technology at its infancy. So this is why we thought that at its very inception, Ignition is a great platform to be thinking about this and talking about it. And to do all of that, I would like to invite on stage Urbasi Sinha, who's a lead quantum researcher in India. As I said, her and her team at the Raman Research Institute have done an experiment that has got global attention and which, as the headline said, disproves Einstein's theory of relativity. That's how important she is. And of the many awards, many committees, many important academic positions that she holds, here's just one indication of how pivotal and catalytic she is that she won the Chandrasekharan Saraswati Award, which has been given to prime ministers and presidents and Lata Mangeshkar and Prime Minister Atal Bihari Vajpayee and President Abdul Kalam Azad and innumerable others. But she is the youngest to get it. When I was looking at that, everybody was 60 and above. You'll see she's nowhere close to that. And she's a woman scientist. And the only other young person in that gallery of fame was Maljur Bhargav, who was anywhere close to her age. So ladies and gentlemen, please welcome Urbasi Sinha. Thanks a lot, Shoma. Am I audible? I think this is.
Thanks a lot. That was a very overwhelming introduction.
No, we are overwhelmed with the knowledge you guys are brokering into into our universe, not the universe.
Sure. Thank you so much.
So, Rishi, like I asked Karthik, that at the beginning, before we even try to begin to decode all the debates going on around this, please help our audience and me understand the realm of quantum mechanics and quantum physics. Why is it deemed almost a realm of fiction? Why is it called weird? Even physicists constantly describe it as weird. And yet, what makes it so powerful that there's a global arms race going on to try and harness it?
Yeah, thanks, Shoma. So, I was thinking you would ask such a question. So we have spent several years in trying to understand quantum physics. So 2 minutes of quantum crash course is a very difficult thing to do. So what I would say is that, quantum is something which, it's an area of physics which becomes relevant when the size of a particle becomes very small, okay? So you, me, everyone in this room, we are all governed by laws of quantum physics. But then we don't really see it manifest in what we do because we are very, large in some sense. So when something becomes very small, like an electron, small particles, a small particle of light, photon, that is when quantum physics becomes important. And so just to give you an example of, what would happen when things become quantum, something which is called tunneling, okay? An example I always like to take. So an electron, when it is moving very fast, it reaches a barrier. It doesn't stop. there is a finite possibility that it actually crosses through that barrier, which is very, very high.
Harry Potter-like.
Yeah. Yeah, exactly the 9 and 3/4. The platform 9 and 3/4 is much motivated by this tunneling phenomena. But Harry Potter does it in reality. But if you and I were to, I've tried this actually, go and hit myself against the wall, I've always come back very disappointed. and my, child who's right here, she was also, encouraged to do this when she was small. Now she doesn't do it anymore. And it never works, right?
So you have a blue forehead, Raika?
Yeah, Raika is, very intelligent now. So these are the kind of things, which, of course, we could also be affected by. It doesn't happen because we are very large. And so these sort of counterintuitive, I don't call it weird because, that's my job. So I don't have a weird job, So it's counterintuitive. So these are the kind of things which make quantum physics different.
But Urbasi, let me push you to make it a little bit even more simpler than that. At its heart, if I understand it correctly, and I'm playing the interlocutor here because I'm at sub-zero knowledge, so maybe that'll help others understand it, is that typically all things that in classical physics, everything has fixed properties.
Right.
But the heart of quantum physics is that particles have no fixed properties.
Absolutely.
Till you actually see it or measure it.
See it or measure it. And so this is something which is very counterintuitive. So, our previous speaker is sitting here and, he's sort of looking at us right now. And I look at my family. My expectation is he's still looking at us. So this is the kind of thing we are used to, that our property, the fact that you are sitting there, I'm sitting here, these are things which are independent of whether this audience is even listening to us or not. But if you think about a quantum particle, it does not have any fixed property unless you measure it. So it can have, a plethora of properties, and only when you measure, it reveals what it wants to reveal. And so it's fundamentally different, let's say, from our, classical reality.
Right. So, again, I'm going to share with the audience that at the heart of this, it's like Einstein said, because he was being challenged, he said, I would really like to think that the moon exists, whether we see it or not.
Absolutely.
But quantum physics challenges that notion that does anything exist unless we see it? Urbashi's refused to let me go down that path, but Vedantic thought says that this is all Maya and this is illusion.
Yes.
I won't take you there so fast. But just help us understand three basic things about quantum, which will help us understand why China, America, and now India are trying to get on top of it, which is that what makes a quantum computer faster than the supercomputer? Why can it do it 185 million times faster than a supercomputer?
Yeah. So now, of course, I just, because I am actually a, practicing quantum physicist, I just want to say that, a quantum computer does not make everything 185 million times faster. So, there are a specific class of problems where this works. So just, my disclaimers will be there as we go on, because I actually make these things in the lab. So I'm an experimental physicist. So the basic idea which makes this quantum computer work is what is called the principle of superposition. Okay, so what is superposition? It's a very interesting topic. So, the fact that some of you are smiling at me, some of you are not following what I'm saying already, but then some of you are following a little bit and not following a little bit. So, this thing that, you can be a little bit of this and a little bit of that, that is what is called superposition. It's essentially the English word, that we are, a mix of various possibilities. And so this is what happens in a quantum particle, like a light switch, it can be on and off at the same time, okay? And so this superposition gives us this, possibility of this particle being in, let's say, even infinite number of properties can exist simultaneously. So this simultaneous existence of infinite probabilities gives rise to this very fast, computing, because it can make use of one of many instead of just one fixed, outcome. Yeah. So this is the principle which makes the quantum computer that fast. Yeah.
Are you with Urbasi on this? Do you understand what she's talking about, or have we? Like she said, are you smiling because? Not really. Okay. So Urbasi, I'm going to be your translator, if I may. Yeah. We were talking about the computers being this fast because at least we know that a computer operates in a binary of 0 and 1. But the qubits, which is the fundamental unit of quantum physics, can be as a 0 and a 1 at the same time.
Absolutely.
am
So
I-
it's a little bit of 0 and a little bit of 1.
So that's why it can do every infinite possibility. It can very quickly analyze all of that and give you all the possibilities, which, think of it as a old cow, a horse cart, in comparison to a Ford motor.
Okay.
Just in terms of speed.
Sure. Yeah, I mean, it is just, just to give you an example, if you have a 50-qubit quantum computer, then you can do something as fast as it would, take an ordinary computer. The time it would take is the age of the universe. So in some sense, you cannot even conceive of doing that,
Right.
using even all the classical computers taken together. So that is what we are talking about for a certain class of problems.
Right.
Yeah.
So, let's bring it down to the here and now. There's a race between all these governments and ours now to harness this, because in the area of communication and cryptography and security, this is a very, very powerful new force.
Yeah.
The moment that somebody really cracks the quantum computer, no information in this world is going to be safe, because that quantum computer can crack anything in the world. So you did an experiment that is going to help, create secure communication for India. So can you talk about that in the simplest terms?
Yeah, this is actually our main, area of interest. So what happens is, so when you have, I see lady in front, she's using a cell phone. So one of the things we are doing using a cell phone is we are doing, buying things online. Amazon, Flipkart, we are always buying things. We are, we are sharing our banking information with a third party. So now the point is that, if you're doing this, currently what we are doing, we are assuming that the information I'm giving is actually only taken by the intended second party. So, but suppose you get hold of this information and you are malicious, then of course my bank account is, gets down to 0. So that is something we don't want. So now, how are we doing this? Of course, we still have some security. What we are currently doing is we are basing this security on certain problems being very hard. Okay, and so this hardness of a problem is very subjective. So something that is hard for you may not be very hard for a very, very efficient computer. And a quantum computer can actually break this security. So this is proven that we can run algorithms which will break this security. And quantum computers are becoming very real. So what we are doing now as a community is we are coming up with a method of doing this security, banking transaction, voting, all these strategic examples. We are doing this by using quantum physics itself. So if you have a quantum threat, you have a quantum solution. And that is called quantum communication. Okay? And so we are using laws of quantum physics now. So it's a paradigm shift in security. So we are, getting rid of the current means. So the whole idea is that we will replace the entire security that we have globally with the quantum analog. And our lab is the first one to work on quantum security in India. And however, if you and I are going to share some information using quantum security is not very interesting beyond a point. Yeah. We want our country to secretly, be able to share something with a friendly country, and some other country which is malicious should not get hold of this information. So the distance is a very important problem here. How do you solve this distance problem? And what we are doing is we are using an out-of-the-box solution where we are using a satellite to, as a trusted courier. So the satellite is interacting with me, satellite will interact with, let's say, Canada, and India and Canada can share quantum security. Right. So this is the, big problem we are attacking.
I just want to draw the audience a little bit back into this conversation, because I'm getting this kind of vibration, that we've lost some of the audience. Is that when we are talking about the qubit, you had a lovely analogy, which is the typical, I don't know the Tamil cinema equivalent, but in Bollywood, you always had that Ram and Shyam, the twins that got lost at birth and could always feel each other no matter whether they'd met or not. So in quantum physics, you have the quantum entanglement, right?
Yeah.
So can you...
Yeah, so quantum entanglement, the best way to explain is by this Lost at Kumbh Mela example, so that has come in lots of Bollywood films at least. And so the whole idea is that these twins, even if one of them is lost and the other grows up somewhere, that's the usual example. They share this correlation because they were born, almost simultaneously. And so this is what happens in quantum entanglement, that two particles, they are born not almost simultaneously, in this case simultaneously, and they share a correlation which they share even if they are separated by thousands of kilometers. And so quantum entanglement is used as a resource in quantum security as well as quantum computers, for instance. Yeah.
Right. So I'm just trying to draw it back to Urvashi's experiment that, you know, the Nobel winner who won that, he proved without, it's called a loophole-free experiment, that two particles in quantum entanglement, correct me if I'm wrong,
No, you're right.
do actually have this quantum, Einstein called it spooky action at a distance, that you do something to Ram and Shyam at the other end of the galaxy is also going to immediately have the same reaction.
Yeah.
Am I right?
And this happens in the movies also, right? Yeah. So you are torturing one and the other is
Feels
feeling
the pain.
So this was a Ranveer Singh film, no? Very recent one called Circus.
Right.
Which happened, where it happened in a very dramatic way. He would feel the electric shocks. Somebody else was getting the shock and he would feel the shock. So,
Right.
so of course, it's a very popular description, but that is what happens in quantum entanglement.
Right.
Yeah.
But your experiment then further went and proved that even a particle in itself, in its solo self,
Yeah.
has quantumness.
Absolutely.
And I was reading all the articles, you know, around praising your experiment, and it said that it actually now completely questions the notion of reality.
Absolutely.
Because you can take this upwards, and there's no reason why it stops at atoms or further. And I read a phrase which literally said, this breaks the legs of the table and chair on which we are sitting, which means that does this chair exist? Does this table exist? Does Shoma exist if you're not looking at me? Is my hair black if you're not looking at it and making it black? So it questions the whole notion of reality.
Notion of reality. Yeah.
So that, now answer that, Urvashi. Are we really sitting in an illusion right now?
It depends on whether you're looking at the audience. I mean, you know, but then, yeah, I mean, you know, the one thing we have to realize is that we are not yet in the quantum domain. So, you know, we are very classical. So we're made up of these quantum particles. But together, we actually still are classical. So, you know, your hair will remain black. But then I think we had this beautiful discussion that, you know, it's because, you know, it appears black to us. But what about bumblebees and things like that? So different animals may have different perceptions of what your hair color is. And so again, that brings us to this macroscopic vision of reality, that, you know, it depends on the observer. So this is what quantum physics is all about. It's all an observer-dependent phenomenon. So it depends on, you know, what you are measuring, what you are observing, what property you see. And so what we went on to do is take this experiment further. So Anton Zeilinger and other, you know, colleagues who won the Nobel Prize, they actually did this for two particles which were separated, like this Ram and Shyam example that we took. But now the question is, why do we need to be twins in order to see whether we are real or not? Even a single particle we need to be able to do. So we did this experiment in the single particle domain. And, you know, we did it in a way that hasn't been possible in 40 years. So in fact, we are very pleased with that, you know, we were able to show the lack of realism for a single particle. Please remember that quantum particles are not real, in the sense that, you know, the properties are only dependent on what you measure. So this is what we went on to show.
I don't know, through this entire conversation, have we kind of communicated the heart of what we are talking about? How many of you would raise your hand and
all
say
of
you're
you
getting
are confused, because that would be the message here. Because, you know, it is very difficult to, I mean, I'm sincerely hoping that you didn't follow everything. I mean, because if that is true, then you are with us. Because, you know, it's an entire field from us. So,
right. No, but I was saying that at least if we communicate this fundamental thing, which is, I would say, like, I would want the takeaway from this session to be two. One is that like I said, why is everyone harnessing this? Is the sheer power of this, you know, that just imagine that we're operating in one choice. The computers are operating on one highway, and here comes somebody that can quickly go zigzag zoom over all the possible highways and give you an answer.
And reach the answer exponentially faster. So this 187 million is an example, but the idea is that something which would take the age of the universe now takes seconds. And so so I just want to give you one or two examples of, you know, problems which actually are getting benefited from this. So as opposed to, say, AI, which is, you know, much more recent, let's say, you know, it was a beautiful topic, but quantum physics is more than 100 years old. And so your phone or whether, your MRI machine, or the fact that, some of us get our eye vision corrected using lasers, these are all because of quantum physics. So it's something that we are all using inadvertently. So just to, sometimes the conversation leads to this thing that, everything is very speculative, but it's actually very real. But having said that, now we talk about quantum computers, and there is a question, are these real? Are they doing anything real? So one of the big things that a quantum computer can do is actually make new materials, okay? And so give you an example, one of the things which we are all worried about, let's say as conscientious citizens, is a clean environment, okay? So we all want the environment to be clean because naturally we have contributed to polluting it. So one is green energy, that is okay. But the other is, you come up with a material which absorbs the carbon dioxide from the atmosphere and just essentially cleans up the environment around you. You don't have such a material, but a quantum computer can help you build one. And this is something which is already being researched globally, clean environment. The other is, for instance, COVID. Something that, now maybe hopefully some of you are following something, otherwise we are doing something completely wrong. But COVID is a situation we have all been through. And so India did beautifully in COVID. We came up with the vaccines, all of us probably are vaccinated, but many countries didn't do it because they couldn't, right? So the idea is that we want to reach, want those vaccines to reach them. So what prevents us? Countries are not next to each other. Transportation. COVID vaccine has to be, in a temperature, certain temperature, and they also expire. So many new conditions are coming in which prevent me from just sending the vaccine to the less fortunate country. So this is an optimization problem. And quantum computers can solve optimization problems way faster than the classical ones. So these are examples, where quantum computers are already being used. So this is not a matter of fiction. And that is why we are entering this race, because we want to use it for social good. I'm actually involved in using quantum computers for social good. I'm working on using it for the Sustainable Development Goals of the United Nations, working with a institute in Geneva for this. And so we are actually, and of course you brought up he was the
doomsayer.
Yeah. So then I don't want to be that, but then any technology has a flip side. And so today I'm trying to make better, environment or give you a COVID vaccine faster. Somebody else will use it to crack my security and take all my, secrets away. So we need to, ensure that we have good governance for this.
Right.
And that is something we are working on. Yeah.
So I just wanted our audience to understand that where are we at in this? I was saying IBM just shared a post about the fact that they have a computer that has 400 qubits.
430 odd.
430. So when we are talking about the qubits, just to help us get more fascinated by this conversation, here is a scientist that's dealing with a material that has to be you have to deal with that material.
The picture that you show is for a superconducting device. So it needs to be at a very, very low temperature for this to work.
Minus 400? Is that? Or
well, it's microkelvin.
Right.
Yeah.
So anyway, but India is now able to harness 4 or 5 qubits.
Yeah.
But America is already, IBM has a 400 qubit strong computer, and it said that in the next 5 years or 7 years, it's going to get to
4,000 qubits.
4,000. That's again that exponential speed coming. It's taken them that long. So help us understand, Urbasi, that India is at 4 qubits, and we're already saying like, wow, you've done something fantastic.
Now is my time to defend the country. What do you do when you're in a forum like this? At least you should go with the impression that we are actually doing very well. So IBM has worked on this for 2.5 decades, and they have been resourced very, very heavily. Now we have a national quantum mission with a certain amount of resource. China has spent billions of dollars on it over the last few decades. So, at some point we need to realize these things take resources. We have produced the 4 or 5 that we have with what we had. But now with this pumping in of some resource, and hopefully others also pitch in, we need philanthropy. Our philanthropists just go and, do brain research and cancer research, but this is actually equally important because it will help the brain research and cancer research. We can come up with new drugs. Drugs for good causes. Of course. So, just because, I don't want to be quoted in new drugs. Yeah. So new medicines, right? So we are, at a very, very important stage where we have a critical, number of people who are working on all these technologies, who are looking at this national mission as something which will catapult us to, the higher number. Because this number is not just about adding, just to make it clear that it is about actually changing the whole structure.
Right.
And so we want to go to, from my thing, I want a global quantum communication network. So the entire world should be connected using quantum security. And so this is a tall, ask. It requires resources.
Right.
And now we can hope to go there, right? So we are doing very well with what we had and with very little support.
Yeah. No, again, I mean, just to bring the geopolitical angle, like China has a 2,300 kilometer quantum secure link already, and we're at like harnessing 4 qubits. And again, I want to play her ambassador for their field of knowledge, is that the qubits, I mean, these particles that we're talking about, for them to exist in these infinite possibilities, they have to exist in a way where they don't get measured, because the moment there's any intervention, you measure it, it becomes something it becomes something you can define, and so it loses its quantum power. So this is a constant riddle that they are chasing, that how do you harness this? Because any noise, as they call it, even an inkling that it is an experiment, it is going to get measured, makes it lose its mysterious quality, So one, you have to do it in that level of cold. Then you have to not let it know that it's getting harnessed. So there's some really fascinating, mysterious aspects.
Just to add to this, you need to be able to access it, but then you need to be able to do it in a way that it doesn't lose its quantum property. So it's like, a constant tussle. Because if you do this a little too much, then you lose its quantumness. And if you lose its quantumness, then there's no point in accessing it. So there are all these criteria which need to be simultaneously satisfied. So it's not, it's not trivial. So that I don't want to
so I want
you how to do it.
I want to take us to a little more popular culture.
Excellent, that's my thing.
So we've been showing this cat right through. Of course,
I have been looking at it, yes.
So it's Schrodinger's cat, which again kind of helped sum this up. Famously, Schrodinger's cat could be dead or alive till you open it and you decide. Then it takes on whether it's dead or it's alive.
So it was there in the Big Bang Theory, right? I don't know whether the audience is familiar with this sitcom called Big Bang Theory. Half an episode was there on Schrodinger cat. So we have made it to pop culture, not me.
Right. But I'm going to ask you that, we're talking about physical experiments, about national security issues, cryptography, communication, computing, etc. But there's a whole universe, and these are very, very serious physicists who genuinely believe that there is a multiverse, that we all have avatars, that this is only one avatar of us, that you decided to marry your husband, but that was a quantum fork in which another version of you did not marry him, and you walked down.
I think another version of is thinking about Aditi Rao Hydari already. So that is a possibility. Yeah, I agree with you. Yeah.
Right. But they're very, very serious people, serious physicists who genuinely believe the multiverse is real, avatars are real. David Deutsch, again, there are all these fathers of these technologies, but the father of quantum AI says that very quickly, or in the near future, we could upload ourselves into quantum computers and see what all our avatars are doing in different worlds. And they all say that the real, which comes to Vedantic thought, that none of this is real. So now tell us, does the multiverse exist? Why is it something that very, very serious scientists are taking as...
So just, this is one of those things. So I actually am an experimentalist. I work in the lab, and I measure things, I know what I'm doing. So I'm a very practical kind of person. So the multiverse is something, so all the names you took, these are all very well-known theorists, okay? So there is a group of well-known theorists who do believe that, this possibility can exist, and they have come up with different notions in that. One thing you may have realized, because you've been, doing a lot of, I think you know as much as I do, in at least the how to explain things. She does a better job. There is no experiment. There is not a single experiment which has been done to actually prove the multiverse. Neither is there an experimental proposal on how you can do that. So, this is one of those notions which it sounds very good, but then as a practical, physicist, I cannot just go and say that, I believe in it, because I only believe in things that I know, I can measure, and I can verify. And, that is, I'm a very boring person. But of course, Hollywood wouldn't use quantum as much as it does if these notions did not exist, right? So, and one more thing I just want to add, that, that's my personal belief. But having said that, there's always a possibility that, we don't really know everything, right? Very few things we actually know. So there's always a possibility that it is in that realm. But then, in my, I'm not a believer of this notion. Yeah.
Okay, we're running 3 minutes late. It's time for cocktails and snacks.
Oh, wonderful, yeah.
Yes. But I'm just going to, while I'm going to call out 1 or 2 questions. Do you want me to, or do you want to break for drinks? Please raise your hands. Questions, okay. So I'm going to ask you to just respond.
Oh, there are questions, oh wow.
Yeah,
I'm thrilled, yeah. Yes.
Yeah. But Urbasi, you said there's a quantum paradox to what you just said. You said you're an experimenter, you're a researcher, and you only believe what you can measure. But the very phenomenon of quantum physics is that it cannot be measured. It loses its quantumness when you measure it.
That's true.
So that is why this entire speculative world is the very heart of quantumness.
True.
So, and your experiment proved that there is nothing real.
There is nothing called realism.
Yeah. So now please address the audience on that.
So of course, yeah, this is a very important question actually. So, the quantumness exists, as the system evolves. But when you measure, it becomes very, very classical. So all these things we talked about, these infinite possibilities of zeros and ones, when you measure, it's either a 0 or a 1. Okay? So this is very important to note that, the measurement actually collapses the wave function. That is the technical way of saying this. So as you measure, you actually can actually measure something which is classical. So the whole quantum mystique, or whatever you want to call it, I don't call it that. It's because I'm a quantum physicist, I become mysterious, and I really am not. So then the whole thing exists till you measure. And so measurement actually collapses the wave function and makes it all classical.
So, some of these questions were actually for Karthik, so I'm going to stop here. I'm going to, let's have cocktails and snacks and reconvene for a session on human creativity. This was on human ingenuity at its most cutting edge. And I hope that Urbasi will be there for us to literally, weigh in, like sweep into her and ask about the mystery of this, that how can you deny that there is no other reality when just by measuring it, we are forcing ourselves back into only what we can see. She told me not to ask about Vedantic thought, but I think it's fascinating that there was this idea that all that we see is an illusion. It was a philosophical thought, and quantum physics is kind of saying, yes, that's true, but we are too shy to say it. So on that note...
No, I think that is where, this age thing that you brought in the very embarrassingly, I think that is playing against me, actually. I just have to grow slightly older to appreciate these things, I just don't seem to have time to think much, yeah?
Right.
So I think that is where I am. I'm sorry about that.
Right. Thank you very, very much, Urbasi. Just as maybe just something enough to make us all go and Google, there was one more point we didn't touch, which is teleportation. We've seen all these movies, Marvel movies, Doctor Strange. Yeah, she's come back. We've seen Doctor Strange. We've seen Spider-Man in the multiverse. We've seen Ant-Man going into the quantum. And we've seen all these fantastic things that can teleport. Well, they do teleport. They do manage to send things where there's no medium, there's no air, there's no airwave, and they're doing it. So this was just this ignition, just the start of a conversation.